My name is Melissa, and I've been working this summer on adapting the forest fire model to biological waves inside cells. And been doing this alongside Abby Bull, who's been guiding me in every step of this process, Dr. Lenny Campanello, who's provided support and guidance and direct help, and Dr. Lissert, who has been my mentor this summer through the Gen program. So the applications of my project really relate to directed cell migration, which is a really important process to study because it has huge impacts or it's integral to wound healing in the body. I have a diagram here of this process because in multicellular organisms, you really need your white blood cells to be able to migrate to the site of damage so that you can promote healing and discourage pathogens. Also very important in embryonic development to make sure that cells end up in the right parts of the body while the body is forming. And cancer cell metastasis is a subject where we see this really get out of control. So the machinery that allows this process to happen is called the cell's cytoskeleton. And one really important protein in the cytoskeleton is called actin. Actin is seen in this diagram as the little red threads that polymerize at the front of the cell and allow it to reach forward into its environment in the direction that it needs to travel. Another word that you'll hear me use is nucleation promoting factor. This is a really general term. It can take the form of different elements in the cell, some of which are NWASP or ARP23, but these just encourage polymerization to happen in actin and allow this to happen. Studying actin really gives you a good idea of how the cell is responding to its environment and shows you a lot about its movement. So actin can polymerize in waves because it's an excitable system, this polymerization process. We can say that because polymerization is an all or nothing response, like an action potential. It either happens or it doesn't happen, and it allows us to see a wide variety of different behaviors. In this giant Dicty cell on a flat surface, we can see spiral waves forming, and it's also important to note that these waves of actin, when they push against the cell boundary, you can see the cell moving in that direction in space. So it really allows you to study its movement. Another really cool thing that I've been studying or working to learn is the way that external cues in the cell's environment can influence this actin polymerization. I've really been working with ridged surfaces and cells navigating those. I just want to show you where these ridges are, but you can really see a huge difference between the ways that these actin polymerization waves act on a flat surface, really large and have their way, whereas on the ridge surface, the waves are much more confined and only allowed to go off in little shoots that tend not to cross perpendicular to the ridges. And the tool that I've been using to simulate this behavior is called the forest fire model. It is a two-dimensional cellular automata model, which is just a really simple model because it is discrete with respect to time and space. You see changes in behavior across frames and pixels. This model is governed by a few simple tenets that I can interpret in the language of cytoskeletal activity, and these give me my simple parameters that I can adjust in specific ways, and different combinations of these parameters can give me these small patchy waves that are quite confined, or these large global waves that really take over the simulation space. And in this model, my green pixels are representative of where the nucleation promoting factor is, and the red pixels, which are a little hard to see at the front of the waves, represent actin polymerization activity. And I can see excitable waves similar to what is observed in cells with actin. In my model, I'm also able to instate ridges, and I just want you to see where these ridges are. But what I've really been trying to study and focus on is the way that the waves in my model are affected when they hit the ridges as they're traveling along this surface I start them in a flat region and then study how they behave in the ridges or across them. I can instate these ridges by adjusting one of my parameters, which is the probability of my actin polymerization activity spreading. So I create regions where it's absolutely not allowed to spread in this case, and you can see my waves are very confined in between the ridges, and I can study behavior based on that. One thing that I've been doing to make my model more realistic to the spreading that we see in living cells is correcting the way that my activity is allowed to spread. So in my original model, I was allowed to either spread to the direct neighbors or to the direct neighbors and the corners equally. And these gave me very diamond-like or square-like spreading in the most extreme cases. But I was able to create more circular behavior, which is desired because you see more circular wave spreading in life, like a drop into a puddle. You see propagation of circular waves, and I accomplished this by considering a much larger area for each instance of activity and correcting the probability of spreading to each neighbor based on the distance away from the central region. Another thing that I've really been working on is modifying the way that my waves spread along ridges. So in life, we can observe that actin tends to have accelerated polymerization in regions of curvature, which really means up the side of the ridges, it's much more likely to be encouraged to move. Obviously, in my two-dimensional environment, I don't have curves or that third dimension with curvature, but I can simulate this by creating thin strips alongside the ridges where activity is encouraged to spread much more. And I can see similar behavior where I have little offshoots over the top of the ridge that are generally much more discouraged as compared with these much larger waves that can have their way in the flat area. I'm also able to take some data based on this. And in my comparisons, I've seen that the front of the wave that is not crossing the ridges is able to travel much more quickly than the part of the wave that's confined or made to transverse the ridges. And as my project continues to progress, I will continue trying to make my model more realistic to what we see in life so that it can be a good tool for interpreting experimental observations. And one direct step that I'm taking is incorporating a system for local excitation and global inhibition, which is an excitable framework that is more realistic to spreading seen in cells. I would also really like to take this opportunity to thank Qishen Yang for the beautiful movies of cells that you've been able to see, members of the LOCERT lab for helping to have my project take shape and welcoming me, and Dr. Daniel Serrano for all of the resources he's connected me with and for his support. Thank you for listening.